Thank you. Am I audible in the back of the room? Can you give a thumbs up if you can hear me? All right. Thank you so much for being here. I'm thrilled to be here at PLMW. So for those of you who I have not yet had the pleasure of meeting, I'm Lindsey Kuper, and the topic of my talk today is reasoning under uncertainty, which is something that we're called upon to do in SMT solving and in research and in life. And I'm especially happy to be at this point in the PLMW program because I think that this talk may serve as a sort of bridge from aspects of Derek's talk before me to some of the talks that are after me and later today. So I'm a newcomer actually to the topic of SMT solvers, and I arrived at it I think via a somewhat circuitous route. So I want to say a little bit about my personal history and how I came to be giving this talk. So during my PhD, I worked on what I called lattice-based data structures, which let you ensure that parallel and distributed programs run in a deterministic way, while still allowing for shared state between tasks. And my collaborators and I proved that our mechanism enforces determinism, and we implemented it in Haskell. And then after my PhD, I spent almost 4 years at Intel Labs, where my colleagues and I worked first on what we called non-invasive domain-specific languages for parallel programming. And by non-invasive, which is a term coined by my collaborator, Jan Vitek, we mean that programming in the DSL feels as much as possible like programming in the host language in which it's embedded. Although under the hood, the DSL code is being separately compiled and parallelized. And we wrote a DSL in the Julia programming language that lets you write code that's automatically parallelized and runs faster than plain Julia. And then, so both this project and my PhD work took forever to publish, by the way. So each one took 3 or 4 attempts to get the first paper out. And I found this especially frustrating the second time, actually, because after we implemented this non-invasive DSL for parallelism in Julia, one of my colleagues at Intel Labs, who was a total badass, used it as the foundation for another Julia-based DSL for implementing deep neural networks, and he published that work at PLDI 16. And the same program committee rejected the paper about the underlying DSL, which I had worked on. So at that point, I was feeling cynical, and I kind of cynically thought, okay, well, I guess I need to learn about this neural network stuff, because apparently that's how to get papers published. So being who I am, though, learning about neural networks quickly morphed into learning about verification of properties of neural networks, making formal guarantees about their behavior. And so at that time, the state of the art for this kind of verification wasn't very far along. So I coincidentally then, that same total badass former colleague put me in touch with some people at Stanford who were working on a domain-specific SMT solver called Reluplex for verification of neural networks. And I had the chance to hang out with them for a year and learn for the first time about SMT solver internals and about the amazing power of domain-specific solvers to attack a problem efficiently. And so by now it's the end of 2017. I'm applying for faculty jobs. My friend Neil Krishnaswamy advises me to make up a narrative that will connect up all these different things that I've done. And so at first I thought, well, how can I do that? They're not connected. No, the first one was about determinism proofs, and then the next one was about Julia, and this last one isn't even PL. But the more I thought about it, the more I realized that there actually was a story that I could tell that tied together all these things that I had done or worked on or learned about. And the theme is that finding the right high-level abstractions to represent a problem enables optimizations or smart scheduling decisions that would be hard or impossible otherwise. In the case of the lattice-based data structures, it was commutative operations on lattice elements. In the case of the Julia parallelism DSL, it was aggregate array operations. And in the case of this SMT for neural networks thing, it was new domain-specific primitives that extended the theory used by the solver. So I realized that there's this guiding principle and goal of all this work, which is finding the right high-level abstractions to express a software system that not only doesn't compromise efficient computation, but actually enables it. Now, of course, this is not at all a novel idea. So it's quite an old idea that gets discovered again and again. So here's a picture I like a lot, which illustrates a way to think about the programming language design space. And if you've seen Kunle Olukutun give a talk, you might have seen it before, because I stole it from him. So the idea is that there's a three-way trade-off between performance, productivity, generality. So productivity means you can write code at a high level of abstraction that's presumably easier for programmers to reason about. And if you decide to optimize for productivity and generality, you get a certain kind of language, of which, say, Python, for instance, is a canonical example. On the other hand, if you chose to optimize for performance and generality, you get another kind of language, of which C is a canonical example. And then the combination of all three of these things is this magical unicorn, right, that you can't have. But a solution to this trilemma that many people have proposed is using high-performance domain-specific languages. And what these people found is that by giving up generality and restricting things to a particular domain, you can have both a high-level programming model and high performance. Because then the language implementation can make more assumptions about what you're trying to do, and it can use that information to make smarter optimizations or scheduling choices. So I find this to be a beautiful idea, and it's kind of at the core of why I think a lot of us like PL. But it turns out that PL people, as much as we might think that we have a monopoly on this way of thinking, we do not. And in fact, SMT solver developers sometimes choose the same trade-offs for the same reason. And my eyes were really open to this during that period of 2017 and 2018 when I was hanging out with the Stanford people working on domain-specific SMT for neural networks. And I hope to take that idea now and try to apply it to building domain-specific SMT solvers to other domains that I care about. So that's how I began to get interested in SMT solver internals and how I came to be talking to you about it today. So over the last 10 or 15 years, there's been a revolution in SAT and SMT solving, and we've seen the effects of that revolution in PL. So there are any number of papers that I could bring up, and I will only have time to talk about like a tiny sampling of them. So applications of SAT and SMT solving in PL include super optimization, which is finding the optimal sequence of instructions for a given computation. There's type checking and inference algorithms, especially for more sophisticated type systems, various other program analyses, high coverage testing and symbolic execution, verification, and today, all of these ways of using solvers are available in what Amina Torlak and Russ Bodiek call solver-aided languages. And so really, there's this nice quotation from Hoyle and Coleman. They describe SAT and SMT as a disruptive technology that allows problems to be solved faster than other known means. And this is from their CACM article in 2017, The Science of Brute Force, which I strongly recommend, by the way, if you want to know how SAT solving works. But what I've observed is that SAT and SMT solvers are useful in PL research and increasingly ubiquitous, but a lot of us, and this even includes some people who I'd describe as power users of SAT and SMT solvers, we view solvers as black boxes with mysterious inner workings. And the solver produces an answer, yes, this formula is satisfiable, or no, it's not satisfiable. But we don't have much, if any, insight into how it produced that answer. Or worse, it times out, right? And we don't get an answer, and we don't know why. So I decided I wanted to open the box and learn more about how SAT and SMT solvers work. And what I found is that the SAT solving process is strangely analogous to life as a researcher. So as Matt Might says, research is mostly about failure. And so too is SAT solving. So SAT solving involves making decisions with incomplete information, learning from those decisions that turned out to be wrong, periodically taking stock of what you know, and determining when to give up and when to try again. So in the rest of this talk, I want to give a high-level introduction to the inner workings of SAT solvers and talk about why I think SAT solving is analogous to life as a researcher. And so I'll be focusing on SAT. SMT, which stands for Satisfiability Modulo Theories, is a generalization of SAT, or if you like, SAT is a special case of SMT. But SMT solvers are built on top of an underlying SAT solver. So everything that I'm saying about SAT solving is relevant to SMT solving as well. And at the end, I'll try to talk a little about why I think it's worthwhile for PL folk to learn about solver internals. Okay, so in order to talk about SAT solving, what it means to do SAT solving, we have to define some terms. So let's say you have a propositional logic formula, like this one. It consists of Boolean variables, negations, conjunctions, disjunctions, and parentheses. So a Boolean variable can be assigned either true or false. In propositional logic, Boolean variables are called the atoms of a formula. So a single variable by itself would be the smallest formula that you can have, and we'd call that an atomic formula, or just an atom. A literal is either a Boolean variable or its negation. So if x and y are Boolean variables, then x and not x and y and not y are literals. Variables can be assigned Boolean values. A literal x is true if the variable assigned that x is assigned to true. A literal not x is true if x is assigned to false. And sometimes we abuse terminology by talking about assigning to a literal, but that just means assigning to the variable of that literal. And a clause is a disjunction of literals. So those are literals connected by an or. So if not x and y are literals, then not x or y is a clause, and so is x or not y, and so on. A single literal by itself could also be a clause. We'd call that a unary clause. And these clauses both happen to have two literals in them, but in general, a clause might have any number of literals. And a formula is a conjunction of clauses. So x or not y and not x or y is a formula, and this is in conjunctive normal form, or CNF. And a formula is in CNF if it's a conjunction of clauses, or a single clause. An assignment is a mapping of variables in a formula to either true or false. And we can say that a clause is satisfied by an assignment if that assignment makes at least one of the clause's literals true, which makes the whole clause true, right? Because it's an or. And we say that a formula is satisfied by an assignment if all of the clauses are satisfied. We say that a formula is satisfiable. Whoops. We say that a formula is satisfiable if there is some satisfying assignment to it, and unsatisfiable if there doesn't exist any satisfying assignment. Sorry, this is clicking ahead. So this formula, for instance, is it satisfiable? Anybody? Yeah, it turns out that it is. So what's a satisfying assignment to this formula? Yeah, so it turns out there are two, actually. We can say either x is false and y is false, or x is true and y is true. Those are the satisfying assignments. You could also speak of a formula being valid, which means that all assignments satisfy it. This one happens to be satisfiable but not valid. And there are a lot of interesting problems that use SAT that boil down to validity checking, but it turns out you can use a SAT solver for that too. You can just take the whole formula and negate it, and then if the negated formula is unsatisfiable, the original formula is valid. So although we're talking about SAT solving, you can also do validity checking with a SAT solver, and that is in fact a common use case. And when we speak of solving a formula, we just mean determining its satisfiability or unsatisfiability, and a SAT solver is a computer program that does that. So how hard is the SAT problem? Well, it wasn't too hard for us to figure out that this particular formula is satisfiable, but in general, it's a famously NP-complete problem. Maybe the most famously NP-complete problem is the first problem proven to be NP-complete in 1971. So there's no known polynomial time algorithm for solving the SAT problem, and indeed the question of whether there is a polynomial time algorithm is equivalent to the P versus NP problem. But of course, the silver lining of NP completeness, in my opinion, is that any problem in NP can be converted to SAT. So this is why SAT solvers are so useful, because a whole lot of interesting computational problems can be converted to SAT, and then you can throw a SAT solver at them. And the NP completeness of SAT notwithstanding, SAT solvers often do a good job on really big formulas. So the SMT revolution came about in large parts because of improvements in solving speed. in the early 90s, solvers could handle formulas with thousands of clauses, and today they can handle formulas with millions of clauses. So the paradigm of SAT solving that I want to talk about is known as conflict-driven clause learning, or CDCL. And the CDCL algorithm for SAT solving is both sound and complete. This means that if you give it a formula, and it gives you a satisfying assignment for that formula, then for one thing, you know that it really is a satisfying assignment. If it doesn't give you a satisfying assignment, you know that there isn't one. So the answers you get back are either, yes, there's a satisfying assignment, and here it is, or no, there is no satisfying assignment. And it's a decidable problem. NP complete, but decidable. So at a really high level, CDCL works like this. It has 3 phases, which we'll call simplify, decide, and learn. In the simplify phase, you simplify the formula you have, and you update the assignment that you have right now. Recall that an assignment is a assignment of true and false to the variables in the formula. And you could have a partial assignment as you go along. So you update the assignment that you have, the partial assignment that you have so far, with any new inferences that you learn. And we'll see an example of this in a second. So you can think of this as the phase that lets you avoid making guesses as much as possible. In the decide phase, you pick an unassigned variable and you assign it true or false using some heuristic. Without getting into the details of decision heuristics, the idea is that you have to make an educated guess about which variable to assign to and what to assign to it. And making a good decision here early on can make solving the whole problem faster. So this is the phase in which you make guesses when necessary. Okay, so you iterate those 2 phases until one of 2 things happen. Either you have a satisfying assignment, in which case, hooray, you're done. Or at least one clause in your formula has been falsified. You made a mistake somewhere. In the you made a mistake case, you've created what's called a conflict, and you need to learn from your mistake and make sure you don't make it again in the future. So you go to the learn phase. In the learn phase, you add a new clause called a conflict clause to your formula. This is the clause learning part of the name CDCL, or conflict-driven clause learning. The purpose of the conflict clause is to prevent the decide phase from making that same mistake again. Or in other words, prevent the solver from trying that particular assignment again. And then you backtrack to the state that you were in before you made the mistake. You go back up to the simplify decide cycle and you keep going. So the learn phase is what allows you to bounce back from wrong guesses. Sorry, I'm clicking ahead. So that's a really high-level overview of CDCL. And I want to look a little bit more closely at each one of those phases. So let's talk about the simplify phase first. The simplify phase does what's known as Boolean constraint propagation, or BCP. It's also sometimes known as unit propagation or unit clause propagation, but we'll stick with the term BCP for now. So here's the idea. Recall that a clause is a disjunction of literals. So the way to satisfy a clause is to make at least one of its literals true. Suppose we have a partial assignment like this that says so x equals false. This is going to make all but one of the literals in a clause false. And it's going to leave that one remaining literal unassigned. So in the clause x or not y here, now x is false and y is unassigned. We call a clause like this a unit clause, and a unit clause is sort of hanging on the edge of being false. The only way to satisfy this unit clause under this current partial assignment is to assign whatever value will make the remaining literal true. So in this case, we have to assign y to be false. So as solving proceeds, it's the unit clauses that are really helpful because they allow us to extend the current partial assignment. In fact, they require us to extend the current partial assignment. And that's called the unit clause rule. Whenever you have a unit clause, you have to ascend the current assignment with the binding that will satisfy that clause. Now, when I was a kid in elementary school, from time to time we had to do these logic puzzles, right? And they'd be something along the lines of there's 5 people, and they each have a favorite subject in school, or they all have favorite colors, or they all have favorite sports. And your job would be to fill into this table, assigning people to their favorite subjects or their favorite sports or animals or what have you. And you'd get a list of constraints which would be something like, Joe likes reading better than any other subject, or the person whose favorite sport is basketball hates the color red. And one of these constraints would give you a place to start from that would allow you to propagate information to further constrain the problem. In other words, one of them would be the equivalent of a unit clause that would allow you to do Boolean constraint propagation. And as I recall, these puzzles were always designed in such a way that you would never have to make guesses and then backtrack if your guess was wrong. So you would instead be able to figure out the entire assignment by propagating what you already knew. And they were also designed in such a way that they had a satisfying assignment typically. So you typically wouldn't have something that was unsatisfiable. But in actual SAT solving, it's possible that during this Boolean constraint propagation, you find out that the formula does in fact not have a satisfying assignment. So if we were to implement an elementary school SAT solver that would be able to solve puzzles like this, then here's how it might look in pseudocode. We take a formula, f, and we create an empty assignment to begin with. And then we do Boolean constraint propagation on the formula and the assignment. BCP repeatedly applies that unit clause rule. So every time we have a unit clause, we have to extend the current assignment until with the binding that will satisfy that clause. So we do BCP, we keep on extending the assignment until we either find ourselves having to assign both true and false to the same variable, in which case the formula is unsatisfiable, or until we run out of unassigned variables, in which case we're done and we fall out the bottom of this loop and the formula is satisfiable. If neither of those things happen, then you give up and you complain to your teacher that the problem is under constraint. So when we were solving those logic puzzles in elementary school, we could generally solve them without having to make any guesses, right? And in other words, the elementary school SAT solver really only has to do BCP. It only has to do this constraint propagation. And we never have to go to the decide phase of the CDCL algorithm, which is the part that makes guesses, or the learn phase, which is the part that allows us to recover from the bad guesses. We just consider what we currently know, and then we propagate that knowledge to extend the assignment until all of the variables are assigned. If we're so lucky as to have a formula that can be solved by just propagating what we already know until every variable is assigned or until we find out that the formula is not satisfiable, if we're that lucky, then this elementary school SAT solver would be good enough. But more generally, we're not in elementary school anymore, right? We're grown-ups and we're going to want to solve problems that may require some amount of guessing. So real solvers have to do something here, right here, instead of give up and complain. Fortunately, what the rest of the CDCL algorithm gives us is a framework for making guesses and then gracefully backing out of our guesses when it turns out that we made bad ones. Okay, so when you solve, you try to do simplification first using BCP, and you do as much as you can. And once you've done that, you go on to this decide phase, where you pick some unassigned variable and you assign it true or false. So earlier I said, suppose we have a partial assignment that makes x false. Where might we have gotten such a partial assignment? We could have gotten it from the decide phase. As the solver runs and we have to make decisions about the values of variables, we can think of those decisions as forming a binary tree of choices. So for instance, for this formula, if we happen to decide the value of x first, that decision is made at depth 1 in the tree. So we say that the decision about x was made at decision level 1. After a decision, we go back to the simplify phase and we run Boolean constraint propagation again. And any other assignments that must be made by BCP, applying that unit clause rule, as a result of a decision at decision level 1, we say that those assignments also happen at decision level 1. So as we saw earlier, when x gets decided to be false, then y has to be assigned false because of the unit clause rule. On the other hand, had we decided that x is true, then we would have to decide that y is true. So after a decision, we go back to the simplify phase, and we run BCP again. And any other assignments that have to be made by BCP as a result of a decision at level 1, we say that those assignments also happen at level 1. How did we know whether to assign x true or false? Well, we don't, right? In SAT solving, just as in research and in life, sometimes we have to make a guess. So we're going to add on to our elementary school stat solver and give it the ability to make guesses. So this version of our stat solver is a little bit more grown up. The part that's in the highlighted box here is the part that changed from what I had before. And this partway grown-up stat solver has gained this new ability to make decisions. It also keeps track of the decision level at which it makes each decision. So any assignments that get made during this initial BCP phase are made at decision level 0. But whenever there are remaining unassigned variables, we increment the decision level, and then we make a decision by calling this, this decide thing here, this decide function, which picks some variable, assigns either true or false to it, and extends the current assignment with the result of that decision. And whenever we update the assignment with a new variable, either by doing BCP or by calling decide, we keep track of the decision level of that variable somewhere. I've left this decide function abstract here, but think of it as using some heuristic that tries to make good choices. So for instance, you could imagine the heuristic might try to do assignments that are likely to make more clauses turn into unit clauses to make solving proceed faster. I don't have time to get into decision heuristics in this talk, but it's a really interesting topic in its own right. So being able to make decisions is great, right? But our decisions aren't necessarily going to be good ones. And once we've made a decision about a variable, there are two options. Either it was a good decision, meaning it'll eventually lead to the formula being satisfied, or it was a bad decision, meaning it'll eventually lead to a conflict when we do BCP again. So what do we do when one of these decisions leads to a conflict? Well, up there, when BCP led to a conflict, we knew what to do. We just returned unsat. But if BCP says there's a conflict after we've called decide, we can't just return unsat, because it doesn't necessarily mean that the formula is unsatisfiable. It might just mean that we made a bad decision somewhere. And if so, it means we need to undo our bad decision and recover from it somehow. And that's what the learn phase is all about. Okay, so suppose that simplify and decide phases have been alternating. Eventually we arrive at a conflict during BCP. But what does that mean, right? Is the formula actually unsatisfiable, or did we just make a wrong decision somewhere? So as we saw, if we encounter a conflict without having made any guesses, we just return unsat. But now if we've made any guesses, we can't just do that, because the conflict we encountered might be the result of us having made a bad decision. So now we need to analyze the conflict and find out what kind of a conflict it is. When we analyze the conflict, we're going to get two things back. We're going to get what's called a backtracking level, which is the decision level that we would need to go back to in order to undo our mistake, if it is in fact a mistake, and a conflict clause, which is a newly learned clause that we can add as a conjunct to our formula to help us avoid making the same mistake again. So let's talk about the conflict clause first. The point of adding a conflict clause to the formula is to help us solve the formula faster by avoiding assignments that we know will lead to conflicts. It might seem a little counterintuitive that this formula that we're trying to solve, that one of the things that helps us solve it is by adding new clauses to it, right? But the conflict clause makes explicit information that was already implicit in the rest of the formula. Importantly, the conflict clause doesn't do anything to change the satisfiability or unsatisfiability of the formula. Instead, you can think of the conflict clause as sort of summarizing information that was already there in the formula and bringing that information up to the top level to make it easier for the decide phase to do its job. So for instance, if deciding X to be false always leads to a conflict during BCP, then the conflict clause might constrain X to be true. And then we won't make that bad decision again. The other thing that we get from this conflict analysis is a backtracking level. And the backtracking level tells us something important about the conflict that we encountered. It tells us whether it was because the formula is actually unsatisfiable or if it was merely the result of making a bad decision. So if the backtracking level is, say, level 2, then we need to undo any decisions made at levels higher than 2 as a consequence. And undo any assignments that were made as a consequence of those decisions. If the backtracking level is level 0, which was our first level, that means we need to go back to the very first decision made. And so if conflict analysis returns a backtracking level of less than 0, it's actually telling us to back up further than it's possible to back up. In other words, a backtracking level of less than 0 means that the conflicts we're encountering aren't actually the fault of our bad decisions. It's just that the formula is fundamentally unsatisfiable. So now we can actually write down the full CDCL algorithm. So now we have our fully grown-up SAT solver. And again, the highlighted part is the part that changed from our last version. So let's look at that part. So whenever we make a decision, we run BCP again. If running BCP after a decision results in a conflict, we call this analyze conflict function, which returns a backtracking level and a conflict clause. By the way, in a real solver, instead of just tacking the conflict clause onto the end of the formula like this, we'd have a clause database that we would add the new clause to, and we would probably also have some sort of fancy, efficient data structure for representing the formula. But this is good enough for pseudocode. So analyze conflict also returns the backtracking level. The backtracking level is the decision level that we have to go back to in order to undo a mistake. So it tells us how far in that decision tree that we need to back up. If the backtracking level returned by analyze conflict is, for instance, 2, we need to undo any decisions made at levels higher than 2 and any assignments that happened as a result of those decisions. And if it returns something less than 0, then we have to return unsat then, because it means that, that in order to satisfy this formula, we would have to back up farther than it's possible to back up. And so, in other words, the formula is unsatisfiable. If the backtracking level was 0 or higher, it means we do have a place to back up to. And so we need to undo the decision that led to the conflict. To do this, we call backtrack here with the current assignment and the backtracking level. And backtrack updates the assignment to remove any bindings that were added at decision levels higher than the backtracking level. We know which ones those are because we've been keeping track of the decision level of every assigned variable. Finally, we update the current decision level to whatever that backtracking level is. We go back up to the top of the while loop, and we keep going from the point that we backed up to with deciding and running BCP. So during solving, the decision level might move up and down, right? It gets incremented every time that we make a new decision, but it might jump backward by 1 or more based on what analyze conflict returns. And this process continues until either we return unsat or we assign every variable and BCP doesn't discover any conflicts, in which case we fall out the bottom of this loop and we return SAT. And that's it. Now you know how CDCL SAT solvers work. So the pseudocode that I have here is pretty similar to the version in Chapter 4 of the Handbook of Satisfiability. I didn't talk really about how decide works or how analyze conflict works. So if you're interested in knowing more, I recommend reading that book chapter. But if you like slides, I can also strongly recommend the slides that Ishil Dillig uses for her course at UT Austin. She's giving a talk at the end of today also. Or the slides that Amina Torlak uses for her course at the University of Washington. So back to this claim that I had about SAT solving being like life as a researcher. So what lessons can we take away here for research and life? So I would argue that part of being a grown-up and being a researcher is figuring out what to do when you don't have all the information and being ready to do something else later if what we did didn't work. So the advice that I can give here is don't be paralyzed, try something, right? Maybe it won't work, but you will have learned something from the experience. And you can use heuristics, which in our case are advice from experts and friends, to guide the search. And expect to fail, right? So that when it inevitably happens, you're not blindsided by it. It's also useful to periodically take stock of what you've learned and summarize that information, which is analogous, I think, to adding a conflict clause to your formula. You're going to have to do this anyway in order to give talks and write that key ideas section of your paper that Derek just talked about. So it's also useful just for your own purposes to periodically take stock of what you know and try to summarize it at a high level. And then there's this question of when to give up and when to try again. So with SAT solving, you try until there's nothing left to try. In research and in life, I don't have a pithy answer to this one, but empirically, based on my own experience, it might take more attempts than you think it will. Don't give up too soon. And so finally, why do I think it's worthwhile to learn about solver internals? Well, okay, so first I think it's fun and useful to know how your tools work. So if you're using SAT or SMT solvers in your work, it can be fun and useful to know a little bit about how they work under the hood. And then I think it works in the other direction as well. So getting back to that guiding principle, I think we could use PL techniques to help make it easier for everybody to develop domain-specific solvers for their own domain. So for instance, my students and I at UC Santa Cruz, along with some of my colleagues, are embarking on this project to help build solver-aided tools for reasoning about distributed consistency that we hope will make it easier to build safe distributed systems. And we call this project Consistency-Aware Solvers and Languages, or CASL for short. And if that sounds like fun to you, think about coming and joining us in the LSD lab at UC Santa Cruz. And that's it. Thank you very much.
Okay, we'll have time for some questions. Anyone in the audience with a question? Don't be shy. Oh, yes.
Hi. So you mentioned that it took a while for your work to get published, or maybe to get to a point where you felt like you could share it with others. What would you say kept you going during that time when you were feeling cynical and feeling like you couldn't really get anywhere?
So yeah, that's a good question. So I would distinguish between it taking a long time to get published and getting to a point where I felt like I could share with others. Because the entire time that my papers were getting rejected, I was sharing the work with others. So I was blogging a lot, I was giving talks, I was sharing drafts of papers. So I was definitely sharing the unfinished work as I went along. And actually something really interesting happened during my PhD where as I was doing this work and these papers weren't getting accepted, I started hearing from, so I was doing all my work I came from PL and I did all my work in the context of PL, but I started hearing from people from the distributed systems world who were interested in my work. And then eventually I started giving talks at distributed systems industry conferences. And then eventually my work did get published. And it was for me, really important to be able to make that connection because I think it's very easy during a PhD to kind of get to be so hyper focused on your own area that you forget that other areas exist. And it was really useful for me to see that although distributed systems people may have had different goals and different terminology and a different culture, a lot of the underlying math actually in the work was the same as what I was doing. So that was really helpful for me to be able to see, and that I wouldn't have been able to make those kinds of connections had I not been putting my work out there before it got published. But I guess maybe to address the bigger question of how did I keep going? Well, I had a support structure, right? So I had an advisor who was supportive. We had a grant proposal that we had written and gotten funded. So I knew that somebody believed in the work, and it just took a while. It took some time for the work to actually get published. But I believed that eventually I would be able to find a venue for it, and I did.
Okay, we have time for one more brief question. If the next speaker could set up in the meantime. Yes.
Yes, maybe one more a bit technical question. So is this algorithm which you presented, is this the main algorithm used by set solvers today, or are there also other algorithms, or do you use a combination, or how does it work?
So SMT solvers typically use a framework that's known as DPLLT, but this is a misnomer. DPLL is actually CDCL. The T part means modulo a particular theory, and it turns out that theory solving can be integrated into that CDCL loop that I showed. So yes, CDCL is in fact what's used by modern SAT solvers.
Okay, thank you very much, Lindsey, for the nice talk.
Thank you.
We are going to